Thank you everyone for joining today. I think it was great context to be set around the importance of marine spatial planning as it was as discussion was happening now. So what I'm about to present today is our tool that we're building on modeling and simulation based marine spatial planning. It's a AI-driven approach. Specifically speaking, it's a physics-informed AI machine learning model that we essentially incorporate into the traditional marine spatial planning aspect. Now, why physics involved? Because standard AI that has been existing for quite some time learns entirely based upon historical data. So essentially presence of marine mammals in a certain region or presence of, whatever data we could capture, that training our model on top of that is what yields the result. But we know for a fact that ocean is extremely dynamic in nature and noisy and extremely unpredictable. And therefore, collection of data in itself is a very sparse and often a very extremely expensive effort per se. And this is where the standard AI fails. This is where the physics-informed AI comes into picture. What we essentially mean by physics-informed AI is the AI is trained on the mathematical equations such as the fluid dynamics or the equations for the acoustic waves or the thermodynamics and so on. So the brain of the AI, as such, what it computes is physics-informed. It understands the reality of the situation. It understands how waves propagate. It understands how. So it's not just a match of capturing what the historical data is and predicting out of that, but rather coming up with a mathematical equation that it tries to solve. Now, before I get into what we are actually building, I think it is extremely important to understand what we are solving for. Now, MSP is not a new concept. It was established in 1980s under the when the project for Great Barrier Reef was established in Australia. It was again, of course, it had a different naming back then, but the core concept remained to be zoning of the region. So zoning of the region so that agencies or stakeholders can utilize it. So by that, what we mean is that if we have the ocean environment, we zone it into what areas can be utilized for wind farms, which areas can be utilized for marine mammal habitat, and so on and so forth, based upon the different properties those areas have. Uh, but traditional MSP and the same practice which has been followed for quite some time now, it essentially relies on extremely isolated set of data sets and multiple agencies coming together to provide that data set. And both in India as well as globally, there has been a issue or there has been a problem of fragmented data. So we have multiple agencies which are collecting data, we have multiple agencies which are collecting different forms of data. A CWC will collect a different form of data, MOES will collect a different form of data, but there's not a single platform where all of that can be put together and it can be analyzed to yield an outcome. And that's what has also been represented in the World Bank report from 2020. If we look at two of the examples of how this actually impacts, in Tamil Nadu, again near the in Tamil Nadu, off the coastline in Dhanushkodi, there were sea walls being installed to prevent local erosion. But the construction of sea walls for prevention of local erosion did not take into consideration how the sediment essentially flows seasonally. So what ended up happening is that that localized fix for that particular region ended up just shifting the problem downshore to a different area, and the adjacent fishing villages lost their beaches, all the turtle nesting in the region have declined, and so on and so forth. And this was being brought out, and again, critics have noted that this is essentially a siloed fix which did not take into account how the sediment flows, how the water flows. Another a good example would basically be the Kerala project. We know that the Biringam project was established a 900 million transshipment hub, which was established without taking into account how construction would affect the local fishing communities. And we know that by 2018, it essentially saw a mass amount of protests that were erupted because again the fishermen were essentially identifying that they lost their fishing hamlet by this particular process or this particular project. Now it was not that the initiative was not planned enough, but the problem was the lack of information or the lack of a single platform where we could predict what the future is going to be. And that's what our modeling and simulation based marine spatial planning brings into picture, which is dynamism and impact modeling. So we wanted to build a tool which essentially continuously adapts to the changing marine environment. So we can essentially see that if we were to provide a particular set of if there's an increase in sea level rise today, then how does that impact the coastal flooding tomorrow? So that kind of dynamism to be able to adapt to the real-time data, was one thing. And the second thing is the impact modeling. So forecasting of different actions, different scenarios, identifying what if scenarios. So essentially, if I have a shipping noise that is being generated, then if I change my shipping route, then how is that noise going to differ in the ocean environment? How is that? And then if by changing the shipping route, and if I can see there's a change in the distribution of the overall ocean noise, then can I then better account for the marine mammal habitat? So such kind of questions can easily be answered by such a predictive mapping tool. And that's why we are essentially shifting from being reactive to being proactive with this particular tool. Now, the overall architecture of how we are going about it, the first and the foremost, the most important layer essentially includes the real-time historical data. This includes the oceanographic data, biodiversity information, AIS traffic. So we ingest all kinds of information and across various different streams. All of that is basically pushed into simulation engine. And as I mentioned, this is where the physics informed modeling comes into picture, where we build a hydrodynamic model to understand how the water flows. That then goes into impact analysis and scenario testing, where stakeholders can identify different scenarios. If there's an increase in sea level rise, then if we take the cyclone Sidar or cyclone Amphan that happened a couple of years ago, now if we want to replay the same event 10 years down the line or 15 years down the line with an increased sea level water or an additional amount of rain, then how would that impact the urban as well as the cropland area in the region? So that kind of an impact analysis is something that this tool provides. And of course, a decision support interface, because it's extremely important that with all of the simulation and all of the modeling and data that we are providing, it is important for stakeholders to be able to use that for making policy. So a decision support interface that essentially provides them all the information that they need. That's what we are building. So this is the MSP tool that we have built. This, as you can see on the left-hand side, there are planning layers. A stakeholder can select from the different planning layers. And on the right, these essentially represent the 6 different initiatives that we have, or 6 different domains that we are covering under the MSP. The underwater noise mapping, the coastal and riverine flood risk analysis, oil spill drift simulation, marine biodiversity and habitat suitability, and so on. I'll explain in depth what each of these essentially mean. But an important aspect to consider here is that we are not just, so the key of the MSP tool that we are building is that we are not just essentially putting AIS data on a map and saying that these are where the vessels are situated. What we are doing is we are calculating the noise that this ship is generating. So for example, in this one, you can see that if you hover over a particular dot, each of those dots represent the ships in the Indian Ocean. You can see what is the ship, with what speed it is moving. But more importantly, the color coding represents the noise that is being generated from the ship. So it's not just about putting there a static map of data, but rather calculating calculating an attribute of interest. So that's one example. But broadly speaking, the first initiative of underwater noise mapping essentially covers modeling the acoustic environment for the complete Indian Ocean region. Now, if we talk about the India's ocean noise floor in general, there are 2 major natural contributions that happen. One is a wind-driven noise, which is basically caused by wave breaking, and also the rainfall impact, apart from the shipping noise. And all the 3 of these are extremely significant in IOR because of the diurnal and seasonal changes that we have in the environment. And we have extremely high rains. We have monsoon that happens across the region. Now, what we do is we model these natural as well as the anthropogenic sources, apply a propagation correction model, as in we construct a channel model that essentially drives how acoustic propagation happens for the signals. We provide to it the environmental factors that impact the propagation of these signals, so the bathymetry, the sound speed profile, and all those things. And that overall gives us the cumulative acoustic stress map. And that's the first module that we have delivered for this thing. And in fact, a lot of presentations that you will be witnessing today essentially covers some of these different topics. I mean, so a large amount of work has already happened in this MSP initiative, while we are continuously adding more and more elements, and the presentations that we'll be seeing today contribute to the MSP initiative in some or the other way. The second initiative is for the flood risk. So there are 2 distinct flooding mechanisms. Again, rivers overflowing from any kind of upstream rainfall, as well as the storm surge, essentially that pushes seawater inland during cyclones. And when they coincide, that is when and this is something that happens in Ganga, Brahmaputra Delta quite often. The result is dramatically much more worse than what either of the catastrophic failures that either of them can alone provide. So this compound flooding is basically a dominant failure mode that we have seen across and throughout the history, and the traditional MSP does not model or account for it. So we basically build separate modules for riverine and coastal search and then combine them using the joint probability analysis. And we then this is where again the scenario testing comes into picture, that now you provide a data of a higher sea level rise. So the hydrodynamic model can essentially take into account how uh, the higher sea level rise is going to impact the overall flooding. And that's what I mentioned by saying that we can replay the scenario of what it's going to do in the next 5 years, 10 years, or 20 years down the line. The third initiative we are working on is coral bleaching and risk forecasting. Now, we know that coral bleaching occurs when sea surface temperature exceeds the local historical maximum by a certain range. But temperature alone is not a factor, is not a driving factor. If we consider just the temperature as an aspect, it generally over predicts where the corals have um, adapted. Now, what we essentially then do is we take into account the other factors. So we created a multi-stressor framework here, which includes aspects such as acidification, turbidity, nutrient loading. All of those are getting combined into identifying the thermal refugia. And what we mean by that is, if we want to conserve coral reefs, we need to first understand which regions are the least impacted and which of the regions are more sustainable for us to first put our effort towards conserving. That's what the broader outcome of this particular work is. The fourth initiative is on oil spill drift simulation. Now, this essentially includes now approximately 40% of the global seaborne oil trade passes through the our basin, and this basic and uh, India again is a monsoon heavy region, and monsoon and waves and everything essentially shift the way an oil travels. So there are two factors that we are considering here. One is to identify an oil leakage, and second to calculate the oil drift. So where an oil leakage is happening and X hours down the line, how that oil is going to drift and spread across the ocean, and how is it going to impact? And this is where, and none of these initiatives essentially are an independent uh, are independent. All of them talk to each other. I'll explain a bit more on that. But just to give some context, like we looked at the coral reef bleaching, we looked at the oil spill drift simulation. Now, oil spills also impact coral reefs, so they essentially talk to each other. So, oil spill drift, like detection of oil spill and detection of the drift of the oil spill, how much area they're going to cover X hours down the line. They also help us inform where the coral reefs are at risk, and so on. The fifth initiative is on the blue carbon and ecosystem health, which is essentially for monitoring the mangrove, seagrass, and salt marshes. Now, these are some of the most carbon-dense ecosystems that we have on Earth, and the Indian Ocean region contains roughly 40% of the global mangrove extent. So we first initially start with an extent and change mapping. So we basically grab around 25 years of satellite data and map out where all we have identified the mangroves and seagrasses in the region. But what the extent alone misses is the degradation. So we want to also identify that what are the different factors that would uh, combine towards the degradation of seagrasses and mangroves. And this initiative essentially is to predict that. The sixth and the final initiative is on the marine biodiversity and habitat suitability. Now, we have quite a few. This essentially is mapping the acoustic habitat for marine mammals across multiple species, blue whales, dolphins, green turtles, snapping shrimps, and all of these are operational at this point. The difference between the traditional and our version of acoustic habitat mapping here is that we do not just look at the historical data. Like ideally, the concept is that you look at historical data of where the presence of these marine mammals are present, are seen, and then you map that into the MSP layer. But the problem with that is that it is skewed by the how much a human can essentially reach out into water and identify. I mean, we essentially perform recording where we are available. It's not about where the marine mammals habitat actually is present. So what we end up doing is we identify the migratory pattern based upon the ecosystem of these marine mammals. So for example, we look at chlorophyll data, which essentially translates to the food, because chlorophyll is required for microorganisms that are in turn food for these marine mammals. And so we track from that perspective and we identify what are the different acoustic habitat for the marine mammals. Again, for snapping shrimp, that basically means that identify regions which are having higher temperature, because snapping shrimp thrive in such kind of region. Now, looking at some of the unique deliverables that we have and the modules that are live today. This tool is something that we've already built. This is the shipping noise mapping, the first initiative that I was talking about. The small dots that you can see represent the individual ship. And of course, as a user, as a stakeholder, you can, of course, zoom in, zoom out, and identify the different regions that are area of interest for you. And the larger heat map that you see represents the overall noise level ranging from 10 to 120 decibels throughout in the region. Of course, you can see the correlation between the extremely dense traffic region as well as the noise that is being generated by these ships and how they are propagating. We've also done some work on acoustic habitat mapping for blue whales, turtles, and snapping shrimps. We have done some work on potential fishing zone mapping as well. This is again live in terms of identifying the high probability fishing zones based upon the sea surface temperature and the chlorophyll data and all those different components. Again, we've seen variation in this across both quarterly as well as across 2 weeks based upon how the monsoon is, based upon which season it is, and so on. As I was explaining, all these initiatives are connected to each other. Mangroves and Flood Risk Initiative 5 from Initiative 5 directly maps to the Initiative 2 of the storm surge. Because again, we know for a fact that the mangroves are the first line of defense for any of the flooding or any surging that essentially happens. The noise and biodiversity aspect, if you look at the what we have generated in the first initiative of underwater noise mapping, that directly goes to the marine biodiversity, because once we overlay two maps on top of each other, we can essentially see which of the region are of high noise level and which of the regions essentially are a habitat for marine mammals. And that one layering on top of each other gives us much more information than just individually these two aspects. Again, that's another advantage of what this tool that we are building. Now, why this matters for India? One is extreme variability. We have like India's coastline face some of the highest amount of climate and human activity variability. And what I mean by that is that we have fishing, we have seasonal fishing, we have festive fishing. Regardless of the season, it is more related to the festive aspects of things. The second thing essentially is the data fragmentation. Now we have a data that is being collected by a lot of different departments, but in separate silos. And as a platform, we want to bring it together in a unifying framework where the agencies can essentially push data into our platform as well as pull data from the platform. So an open model where multiple agencies can come and contribute together. The third is the resource constraints. Again, even if we were to do all of this work using like real world data or calculating the real world data, it is extremely costly. So blanket deployment of sensors for recording the data is not something that is feasible for developing nations. And the fourth essentially is the governance complexity. Today, there is no single marine special planning authority that exists for India. Tomorrow, when we essentially look at policies, tomorrow when we look at the international exposure for India as well as other countries, we want a platform where they can rely on to derive these policies. And we have built this MSP platform to be exactly for that purpose. So that's what we are envisioning by 2029, that we'll essentially have a unified simulation-driven platform. More than 50% of this is already ready, which we are launching soon. And yeah, that's pretty much my presentation for the day. Thank you.